So I'm Brian Cairns, worked here quite a while. And so George will tell you that what you really need for a good talk is a good joke. But I didn't have a good joke, so I put the tie on. It seemed to work really well with almost all of you. So now you take it. So this is sort of the primary qualification for being a project scientist. You need plenty of blue shirts and ties.
You look like a joke.
See, you had to stand behind me to say that. So Jacek and I are going to talk about this PACE mission, which has it's a horrible acronym because it's sort of the pre-other mission, which may or may not happen. But anyway, PACE is primarily about ocean color. And since it's in what they call pre-formulation, the nitty-gritty of launch dates, exactly what kind of polarimeter they may or may not have, and those kind of things are not really cast in stone. The thing that is going to happen is they are going to have a good ocean color radiometer. And so we'll talk primarily about that with a little bit here and there about what a polarimeter may or may not be for this in this particular instance. So notional mission concept, you have your satellite, you have your ocean color radiometer, and the people down at Greenbelt have been lobbying NASA for a long time to have an ocean color instrument that will do the job the way they want it done. So it's not motors, it's not gears, it's not something that can do everything for everybody, but actually has really good performance for looking at oceans. And the key thing for them is that the signal coming out of the oceans is very small, and so you want a very precise instrument. And this is something that Modus and Mears have never really given them. It's the sort of thing that they did get from CWIFs for a very long time, and that instrument was also very, very stable, to the point where you had missions, instruments like Ceres, which are supposed to be very well calibrated, comparing themselves to the CWIFs instruments to show that they were as well calibrated as they thought they were. So the ocean color people did a really nice job of keeping that instrument well calibrated, developing things like lunar calibration and using the moon as a stability source. So instrument payload, there'll be an ocean color instrument, and then polarimeter and those little bullets there. This was the guidance from NASA headquarters to Goddard Space Flight Center, which are tasked with putting the mission together. And the options they have are no polarimeter, because they don't have enough money, directed to JPL, which is Dave Diner's group that's been building an imaging polarimeter for airborne operations and proposing for the last 4 or 5 years. Competed, but GSFC excluded, or contributed, which, of course, if you're the project at GSFC, definitely your favorite because you don't have to spend any of your money on them and you can sort of have lots of reserves. But exactly how the whole polarimeter thing will play out is an entirely open question at this point.
Can you please summarize these instruments?
Let me see how many slides it takes to get there, and if we don't get to what the instruments do quickly, I'll summarize.
Why exclude GSFC?
So this is on camera, isn't it? I'll
We'll
tell
be
you
on
another
live.
time.
We don't have to upload it.
Okay, so the reason that people are interested in ocean color is primarily related to carbon budget and understanding processes within the ocean and how they may respond. So you have concentrations been increasing, so humans are putting carbon into the atmosphere, the oceans both sequester carbon, and also there's plenty of photosynthesis going on. Turnovers of carbon stocks in the ocean are very rapid, and so oceans can actually respond very quickly to changes in temperature, salinity, and anything that's going on. And so phytoplankton, 1% of global biomass, but half the net global photosynthesis. So they do a lot of work in terms of processing gases out of the atmosphere into the ocean, and then a lot of the gases obviously get back out again. Right now, how phytoplankton respond to ocean temperatures is an open question. On the right-hand side, it's showing the permanently stratified oceans and how chlorophyll tracks with temperature and southern high latitudes and northern high latitudes. And there was a paper in Nature by Mike Barenfeld showing how phytoplankton concentrations were tracking with temperature. However, without measurements that allow you to diagnose why things are going on, it's a correlation rather than a mechanistic understanding of why phytoplankton populations are responding to temperature the way that they do. So, the objective is, for the ocean color instrument is, at this point I guess I should talk about measurements. So the ocean color instrument would be a spectrometer through to around here. And so Jacek will talk more about this. And then a few discrete bands further out, because clouds get in the way. You might as well do something about clouds while you're looking at the ocean. It's always a baby in the bathwater thing with the ocean versus atmosphere people, right? For the atmospheric sciences, the atmosphere is the baby and the bathwater is the ocean. And the ocean people, it's the opposite way around. They really don't want the atmosphere. Suffice to say, the measurements would run from about 380 nanometers out to about 800 or 850 nanometers as a spectrometer. And the reason for that is you have, so this is sort of Rayleigh, you have all this variability in your absorption of phytoplankton. And I think, and also around 660, 670 nanometers, there is fluorescence. And the fluorescence gives you an indication of stress on the phytoplankton. So that gives you an indication of whether the phytoplankton are being limited by nutrients, and you can sort of try to diagnose whether temperature or nutrients are the big issue in driving the phytoplankton populations. And then the color business comes down to all of this variability here. Right now, what's done is primarily color ratios from here to 550 or 440, and it's an estimate of chlorophyll A concentration. But different phytoplankton have different colors to their chlorophyll because they're slightly different functional groups. And so the objective for the ocean color radiometer for this mission is to be able to differentiate between different functional groups. And if you can do that, then you can see changes in the functional groups and how that's affected by changing temperatures and also fertilization. So if you see different amounts of iron fertilization and stress, you would expect to see a change in the functional groups of dominant phytoplankton. So requirements flow down. This is sort of not something that we usually think about very much here at GISS. You get the products and you use the products, but this is just looking at if you want to be able to differentiate all of these little wiggly lines, how fine a spectral resolution do you need, and how accurate do you need each of those spectral bins to be? And so that leads you to looking at needing 5 nanometer resolution data for oceans. And so the oceans are driving the bus, and they will do what they do. But for atmospheric remote sensing, if you have 5 nanometer resolution measurement, that's pretty good. You're going to be able to get between water vapor contamination. You can use the O2A band to do cloud height and cloud physical thickness estimates. So there's a lot you can do with 5 nanometer resolution data from an atmospheric sciences point of view.
Is that the longest wavelength, upping into near infrared?
No, they go into the near infrared, and so I'm deputy project scientist for atmospheres. So it's my job to encourage them to add into the near infrared and the shortwave infrared, because otherwise you have no way of tying any kind of cloud record. Like, first of all, you can't do droplet sizes or ice particle sizes. And if you don't go beyond 700, you're sort of hard-pressed to really do a good job in aerosol retrieval, so you won't be able to do atmospheric correction anyway. So our job is to encourage the use of the longer wavelengths.
Why don't they? I mean, is the instrument that much more expensive, or is there a primary trade-off?
I think right. Well, it makes it more expensive. Yeah. If you're going from 380 nanometers out to about 800 nanometers, then what you can do is you can have that be a spectrometer. So you just have a single optical train, and what they'll use is a 2D array, and you'll have color in one dimension, and then they have a scanning telescope, and what you do is a thing called time delay integration, and as the telescope moves, the box that you're collecting stuff in moves with it, and so as opposed to something like MODIS where you just get an instantaneous snapshot, your snapshot moves across the focal plane, but you're continuously integrating, so you can get signal to noise from a sensor like this that's orders of magnitude better than current instruments. So that's great. That's all in one instrument. To do the near infrared, you then need to have a pickoff and have basically a separate back end in the optics. So it does make it more expensive. And if you are going into the near infrared, where you can estimate things like droplet size and ice particle sizes, where you have ice water absorption, generally you need to cool those detectors down to about 160 Kelvin. And so that's expensive. Anytime you have a cryogenic system, that's a cost of money. So there are trade-offs.
Kind of cold.
Yeah, what temperature is up there?
Space is cold, but it's expensive because you want your instrument and your optics to be operating at room temperature. And the reason for that is it would be incredibly expensive and difficult to align your optics at the cryogenic temperature. I mean, you could in principle do it, but usually you want to do all your alignment of your optics and your system at room temperature, and then operate the instrument at room temperature, and then have the detectors cold. And that means you have to have usually you'd have sort of a vacuum system, so you can test it on the ground, where and then you have to thermally isolate the detectors. So to get a quarter watt of cooling for a little rinky-dink detector would usually take a big plate cooling to deep space, unless you start to have active cooling. And active cooling, again, is a money issue, it's a reliability issue, and it makes the design harder. So it's just one of those things that, however you do it, it costs money. It's not incredibly hard, it's just, it will cost money.
Isn't there another answer to Gavin, which is the sun is bright?
The sun's bright, but you usually have, the nice thing about low Earth orbit is if you're in a sun synchronous orbit, then one side is always hot, the other side is always cold. It's when you have...
So you put your detectors on the cold side, is that?
Yeah, so you put the radiation on the cold side. Precessing orbits are a lot harder because then you're sort of moving, the sun flips sides and then you flip the spacecraft, so life can get quite confusing if the spacecraft's flipping and because then you're integrating the other direction.
When you're calibrating, is it the low temperature you're after, or is it like the absence of water vapor and other things in there?
No, it's in the shortwave infrared, the detectors don't work when they're not cold. You don't get a signal. When you're at room temperature with mercury, cadmium telluride, it's not a detector anymore, it's just a diode. It makes a lot of diode noise. Once you get it down below about minus 70 degrees Celsius, it starts working like a semiconductor, like a silicon detector. You have a band gap, but above that it's not working as a semiconductor.
Welcome.
What's that?
Welcome.
Welcome.
But you just told the whole world, man.
It's on the sticker on the computers.
What's the Orga design? Mentioned in the slide.
Okay, so the Orca design is the bit that they've already done and tested on the ground is the spectrometer piece. And they have a rotating telescope, and then they derotate, and they have a very well defined square pixel and they can do a huge swath width, and that's the design right now. And you can put in the infrared back end. You just have a pickup at around 800 nanometers where you do a spectral split and take everything longer than 800 nanometers into a separate system. So you can see that this was the slide that Chuck McLean from Space Flight Center put together. To the now, this is obviously designed to highlight why this mission is going to be absolutely fantastic. Because right now you only get the black stuff, and with the new instrument you get all of the other things: fluorescent line height, color dissolved organics, calcite concentrations, net primary productivity. You know, all the things that you would like in order to really constrain what's happening in the ocean and how much carbon is going there and why it's going there.
Is that accurate?
I could go through it. Yes, yes, no, yes, no. I mean, so some are already demonstrated, some are likely, and some are a lot trickier, like trichodesmium concentrations. I think you'd really. That's.
What was that again?
You wanna-
A species?
It's a particular species.
Which has a
So
weird signature.
I'm not sure that signature is sufficiently unique that you'd be able to say it's specifically trichodesmium. You'd be able to say that it's part of a class of phytoplankton, but whether you could be
And
that
why
specific.
why are they only separating out this one, this particular one? Not,
I
for
think-
example, the major classes which are diatoms and
I-
copolithophores.
Yeah, I mean, I would say it's a mistake in the chartmanship, right? I mean, that's.
Or maybe it does have higher accuracy for such a measurement and not so
It
much
may.
for the others.
It may be that, or it may be
Too
that Chuck was particularly interested in the part of the ocean where that's the dominant.
Calcite concentration would be very good. I mean,
Yeah.
that would be
For
really
acidification, definitely.
very interesting.
Seed dome as well. I mean, all this, the red list there, it's a dream world for ocean carbon. It's
Right.
dream
So
world
that's why the important thing for that is pushing into the ultraviolet.
How much of the ocean does it see? Like the top centimeter?
No, you have contributions deeper into the ocean than that.
It goes down to euphotic depth, so approximately 100 meters, maybe 150.
It's very
Yeah, I mean,
clear.
most of your contributions.
No, euphotic depth. There's no
In the
100
blue.
meters. Huh?
The blue, not
In the-
not in
Yeah, I
green.
mean,
Okay.
so if you look at the absorption spectrum of water, by the time you get to 865 nanometers, you've seen the top couple of centimeters, and then you're getting deeper and deeper as the water absorption gets less and less. So at 555, you want maybe 10 meters contribution, and then by the time you're deep blue, on the order of 100 meters. No, let's just skip that. synergies between ocean color and the atmospheric science we want to do, in the sense that they don't want the atmosphere at all, and we do.
And because some of the feedbacks that we are very interested in, you want to have coincident measurements of like radiation and aerosol distributions and so forth.
Yeah, and the
Clouds,
amount of
etc.
absorption in dust, so you can try and estimate ion deposition rates.
Is this on the table still?
Yes. So,
She missed her first slide.
oh, okay.
Sorry about that.
So the
I will be yes. Thank you. Good news, thanks.
But, okay, so I didn't, the contribution business, right now, what's on the table is, the Dutch might build one, ESA might sort of kind of donate one, might get directed to JPL, and they've not decided whether to go out to industry or not. And that's sort of, getting a nice little political football that's getting kicked around.
So the issue is who's funding it. It's decided that it's going to be there, but the question is
No,
who's going to fund it.
it's not decided it's going to be there. It's still an open issue. So the way that, okay, so I can say this because this is in the letter of direction. NASA headquarters told Goddard Space Flight Center, here's $800 million. You need to do this mission. This is a total life cycle cost cap for everything: launch, ground system, science team, data processing, polarimeter, whatever flavor you like. That's it. You have to at decision point B, whatever that might be, which is around the time that you're supposed to understand everything about the mission and have a plan for it. You need to have a total life cycle cost that is going to allow you to build the whole thing, and you've got to have confidence interval that you can definitely fit within the cap. And so whether the polarimeter fits within the cap or not is something that they're working on right now. That depends on things like how much does a launch vehicle cost, how much money is taken out for science. You want to have, you don't want to launch an ocean color radiometer and a polarimeter and have like a cup of coffee for the science team.
Which you usually do.
Which is the norm, sort of the norm. So all of those things are what they're working on.
Yeah, NASA isn't allowed to buy people cups of coffee anymore.
Well, that's true.
Not even that.
So the science team, they come free.
So $800 million, like, in the scheme of things, like, is that a lot? I mean, because I just, can you give us an example of another mission? I mean, it sounds like a lot.
How much did Aqua cost or something?
Oh, no, how about the one your mission that we lost? What was that?
That was about 450 million. So an instrument of the class of ocean color radiometer is an expensive instrument. Since we're taping this, I don't really want to talk about this, but it's suffice to say it's not a done deal that money gets sent to Goddard and they can definitely afford to buy a nice polarimeter for JPL. It's not a done deal. It's one of those things where they need to figure out how much is each element going to cost, and is it all going to come in on time? Because time is money, right? Once you've got people working on the project, you pay them, and you can't just send them away for 6 months while somebody fixes something. So that's part of what this pre-phase A, whatever they want to call it, is basically figuring out what are you going to do, how long is it going to take, who are the guys who are going to be risks, so you can sort of keep an eye on them and have decision points where you decide, okay, that's really not working, we're just going to cancel it. So that's where we're at now. Okay, so polarimeters, it's nice nice for droplet sizes. This is something that Mikhail did for Recaro, and that's why we like to have a polarimeter on this mission. So to get at things like all of those fancy little bubble bumps, you really do need very good atmospheric correction. You need to know your water leaving radiance is what they want, like on the order of 1%. 5% water leaving.
Water leaving.
So that's pretty challenging because the signal's only 10% of the light that you see at the top of the atmosphere. Okay, I was saying candidates for the polarimeter specs, 3MI or MISP, if they go out to industry, companies like Raytheon and Ball might bid in, and Vanderlei Martins at UMBC could also probably bid in as well.
And relative to your polarimeter, what are all these?
Oh, okay.
And why not yours?
GSFC is not allowed to compete.
Why?
So can you take your designs and
camera
just
off.
ship them to Europe and then Europe built it, or is it proprietary?
Let's form a company.
Okay. So,
Moving right along.
thank you for all the interest.
That's what we're really here for.
So the candidates are Specs, which is a Dutch instrument, and we actually work with that group. It's Otto Hassekamp and a group at what is it, Space Research Organization in the Netherlands, ESRA?
Yes.
Yeah. And so that's a pretty nice design. What they do is you take a very high resolution spectrum, so you're solving the color at maybe 1 to 2 nanometers, and you modulate the color with the polarization. So the wiggles you get on the spectrum are a measure of how polarized the light is. And then you stick that through a polarizer at the back and you split it, and the difference is the polarization, and the sum, the wiggles go away, and you get the spectrum. And it's no moving parts, it's pretty accurate. At least, they demonstrated so far that it's quite accurate. It is something that's been used in astronomy, and it's pretty immature because they've not flown it on a plane and they've not made the measurement over the spectral range. So it seems like it's got that it's a very good technique, but demonstrating that it's going to work over the full spectral range of interest is what they need to do over the next 3 months in order to convince NASA that it's really the way to go. And so that's what they're doing right now. They're visiting Goddard Space Flight Center in April to sort of talk through this. And actually, it's interesting. So Specs is from the Netherlands. That's spectral modulation. And then MISP is Dave Diner's instrument, and that uses temporal modulation. So you have a very fast-moving retarder, and you have another very fast-moving retarder, and you get a beat frequency, and that modulates the polarization so that your modulation is much faster than the spacecraft moving over the ground. And so you can estimate the polarization by looking at that time-varying signal. And the reason that those kind of techniques are nice is that you get a measurement that has a guaranteed accuracy. 3MI, you have a filter wheel, and the filter wheel rotates, and as the filter wheel rotates, the satellite moves. You look at different points on the ground, then you take a difference of measurements that are on the filter wheel, and if the ground's changed, the difference can be just that the ground changed, rather than it actually being the polarization and providing you a measure of what's above the ground, the aerosols or things like that. So with things like Specs, MISP, or my instrument, you can actually have a guaranteed accuracy of the measurement, and then it makes it a lot easier to do the retrievals. With something like 3MI over land, you have no guaranteed accuracy whatsoever in the linear polarization measurement. And both MISP and Specs techniques come from astronomy, and actually come from Keller, right? Was one of the guys. So it's a Dutch guy was instrumental in developing both techniques, and Dave Diner sort of took that from the astronomy books and made it work for a low Earth orbit.
But your whole spectrometer sounded like it was like visiting pixels and moving around. Does not suffer from that problem?
No, so you get the spectrum all at the same time. There's no moving parts. You get the full spectrum, and then you look at how the spectrum is modulated, but you don't have any motion. You take that spectrum, and the spectrum is the spectrum of a particular one point on the ground, and you can make it as an image. So then you get the spectrum. So again, you have a 2D focal plane, and you get the spectrum in one direction and the coverage in the other direction. And you get a spectrum for each point on the ground.
Without complicating this too much, is multi-angle and swath differences, or are those differences an issue between these instruments? Like
Yeah.
the number of angles?
Absolutely, yeah. So 3MI, it's a camera. It's like a camera you could buy at the shop. You got a wide field lens. You get very wide swath coverage. You get a lot of angles simply by taking a picture, waiting 20 seconds, taking another picture, and then you look at the places that you saw the same point on the ground from the different pictures. So very simple, not necessarily very accurate, but very simple, very wide swath. Specs, the Dutch implementation, they think that they can get a pretty wide swath. Again, that's to be determined. Right? That's the current instrument that we're going to be flying with on the NASA ER2 has a very limited, very narrow swath. And MISPI is intermediate. It's sort of like a miser kind of thing. So
And your instrument had a narrow swath,
yes,
right?
very
It's
narrow.
original, very
Yeah,
narrow.
yeah.
So it seemed, anyway, I just want to give a general impression for someone sitting in a lot of these meetings about ACE and PACE that there was really, without the developed algorithms for retrievals and how this data was actually going to be used, it was really hard to prove that you needed exactly this accuracy or this many 100 angles or this many, and so it's really, and these polarimeters are really like apples and oranges and bananas. They're like completely different from a little bit. That was my impression.
Same with bananas. Yeah, so more to the point with Anne's comment about number of angles. All of these instruments, you have multiple angles to try and figure out what the composition and the size and the shape of the aerosol
A lot of
is.
information there.
And how many angles is something that people discuss or perhaps even argue about. And somewhere between 5 and 20 angles is about what you need for aerosols. And specs and MISPI, you have to have a camera for each angle you look at. So that's a complicating factor and makes them more complex than having a simple camera with a little rotating filter wheel. But again, that doesn't give you the accuracy that you'd like for doing the job that you want to do. Did we get to your slide yet? Yes.
So it's conceivable that none of them will pass muster.
Yes, it's conceivable. I think headquarters has a strong desire for there to be a polarimeter. So, but it's conceivable that none of them will fit within the constraints of cost, risk, schedule. Right. So 3MI is, you know what it's going to be. You might not like it. You know what it's going to cost. They're already building 3 of them, actually 4 of them for UMETSAT. So that is what it is. MISPI and specs are, you're not quite sure what the cost and risk profile is, but they're more accurate. And if the Dutch government says they're going to give you one, maybe you do it. But it really is an open question.
But if there's going to be 3 of these polarimeters on geostationary orbits, right?
No, the 3MI instrument would be on a low Earth orbit.
Oh, the UMETSAT is polarimeter.
Well, UMETSAT is the agency, and they have geostationaries and low Earth orbit, but the 3MI instruments would be on the low Earth orbit, 9:30 AM polar orbiting.
So you could still use that to do the aerosols, and this wouldn't be connected to the ocean current.
Yeah, I mean, so you could do something with aerosols with 3MI. They're going to have a really nice ice instrument on that platform, but you wouldn't be able to do anything with atmospheric correction of the ocean color. So I mean,
Which would really
so whether the polarimeter happens or not, Jacek and I are sort of interested in trying to use the ocean color instrument, try and do the atmospheric correction for the ocean color guys, but then we'll take the atmosphere and do atmosphere things with it. I mean, because CWIP has a pretty nice aerosol product, given that it's only got one view angle. Because it's a very stable instrument.
So better any polarimeter than none.
But good to have something. I mean, it's a whole. You've got a platform there. There's plenty of space for another instrument. So if you can fit an instrument within the cost, then it would be great to have one of them.
Well, what is the timeline?
There isn't a timeline that's officially released, but it's 2020s before you'd launch something like this. I think probably 2022 would be my guess. Okay, so we can talk through all of that. Natasha was commenting on the ion content and its effects. Let's try and get to Jacek's slides. There we go.
So what resolution are we going to have near coasts? Because that's one of the regions that I think a lot
Sit there and
of...
answer the
we don't know ocean color very well even right now, even with the instruments we have right now. And that's one of the biggest changes in the future that we are going to have with the best ocean color cycle. And a very big societal impact area, the coastal regions, that's the runoff, etc. And what's happening there, what's the resolution of that instrument going to be?
It's not decided yet. So NASA headquarters is supposed to. So that's a difficult thing for people working on the project. Right?
Does it say 1
NASA
kilometer up there? Does it say?
This resolution in 1 kilometer, I mean,
That's probably what is
Yes.
going to be required. But if that's what's required, then they may go to 500 meters, so that they're well away from the headquarters requirement. Because the way the game is played, headquarters holds the level 1 requirements. If you're not going to meet those, so you better have plenty of margin against whatever headquarters
Because
says
you
you've got to do.
don't want to send up an $800 million instrument that doesn't do what scientists need.
Right. So they don't. So like I say, it's not decided, but it looks like 500 meters is likely. And there are two aspects to coastal. One is you want the resolution. The other is that because it's a narrow strip, and there are these things called clouds. If you don't see that narrow strip frequently, then the clouds can actually drive how well you can do the color of the coast. So if you have a broad swath so you see it every day, that's almost as good as having 250 meter resolution, but only seeing it once a week, because the clouds actually drive how often you can see the coastal features.
so the threshold is between actually 1 and 2 kilometers, and as Brian said, you might be sampling actually at a lower resolution, and that is a requirement that has to be met. And you also have goal questions. So these are, well, let me start it a slide back. So what I'm going to talk a little bit is about the science that has already been done, and meetings that have already been taking place, and the science that was discussed there, and where we are at now, and at least from our perspective, from the GISS perspective. It's me and Brian and Bastian and Andrzej and Michael are also working on that. So these are studies conducted within the context of the PACE mission, and of course Brian talked a lot about that, and it was formally introduced in NASA's publication on Earth observations in 2010. And shortly after, NASA convened a science definition team to define the science and instrument requirements for this mission, and it was decided that by that team that the primary focus would be the ocean science, and the secondary focus would be on the atmospheric sciences. And this table here provides a summary of the threshold questions for ocean sciences and atmospheric sciences. And threshold questions are questions that need to be answered in order for the mission to be a success. And they focus for the ocean science on biochemical and biological processes in the ocean, and for the atmospheric science on maintaining heritage data for aerosols and clouds. And in addition to that, you have the goal questions, and those are questions that you would like to address, and they require enhancements to the instruments. And for the atmosphere, they focus on the interaction of aerosols with clouds, interaction of aerosols with oceans, and also how aerosols affect the climate. That's a secondary goal, or that's a goal question. And for the ocean, they focus on the coastal regions. And for that, for instance, there they would like to have at least a spatial resolution of 500 by 500 meters. But that's a goal question. That's not a threshold question. So, as I said, some of these goal questions require enhancements of the instrument, of the ocean color instrument, the basic ocean color instrument, which is shown here, and I'll talk a little bit more about it. And one of the enhancements that they would require is, for instance, to also have multi-angle and multi-spectral metric data, the 3MI kind of data. 3M stands for multi-angle, multi-polarization, multi-spectral. Therefore, it has the 3M. And in this talk, I'll mostly focus on the ocean science. And for this science, what I want is hyperspectral measurement obtained between 350 and 800 nanometers, and obtained by an imager, and also 3 bands at longer wavelengths obtained by an imager. And the visible measurements here, they are used to obtain properties that are listed here, phytoplankton properties, which are then used to answer the goal questions, or the questions and the objectives that Brian talked earlier about. But in order to obtain these properties here, you first have to retrieve the water-leaving radiance, and you have to retrieve that with an accuracy of 5% or better in the visible part, and 10% or better in the UV. And that puts a lot of constraints on atmospheric correction, because the ocean contributes typically less than 15%, about 10%. So of that 10%, you have to get it as accurate as 5%. So very, very small, 0.5% accuracy. So that puts a lot of constraints on atmospheric correction, how to accurately account for the atmospheric scattering contribution, so that you know then what the remaining water-leaving radiance is. Now, the approach usually followed for atmospheric correction, it is how they call it, is to use radiances in the near-infrared in the sphere at the longer bands, where the ocean is essentially black, and to use those radiances to select an aerosol model. That aerosol model is then used to calculate the atmospheric scattering contribution in the visible part of the spectrum, and then they subtract that atmospheric scattering contribution from the total signal. What you have left over is then, of course, the water-leaving radiance. But the problem with this approach is that it is very difficult to constrain aerosol absorption, and that can lead many times to this kind of situation where you are underestimating the water-leaving radiance obtained from space when you compare it with in situ measurements. So that's a big problem here. So why they are adding UV wavelengths, one of the reasons why they're adding UV wavelengths is that it provides extra constraints for the aerosol absorption, and hence to avoid problems such as this one. Now, another concern or point of interest, as you pointed out, is retrieving and characterizing color dissolved organic matter, CDOM. And those are essentially complex organic chemical compounds that are produced by a variety of processes in the ocean. And they affect the ocean in such a way that they can sometimes be mistaken with an amount of phytoplankton. And so sometimes anomalies in these amounts that are shown in this picture here are very well correlated with estimated amounts of CDOM. And so you want to better constrain the CDOM so that you get rid of these anomalies. Now, that is the reason why they are looking at also at the UV wavelengths, because in the UV what you have is that CDOM becomes very absorbing, and that is also what Brian mentioned. And so what you hope is that you get a large sensitivity to this variation in absorption by CDOM, and therefore can characterize CDOM, and therefore can account for it, and therefore can reduce these anomalies when you want to really obtain CDOM or functional types that Brian was talking about. So that actually poses a problem, because on one hand you want the ocean to be bright enough to do atmospheric correction in the UV, and on the other hand you want it to be you want it to be dark enough to do atmospheric correction. When you're doing atmospheric correction, then you want to have an as least interference of the ocean as possible. You want it to be dark so that you analyze the radiances, either in the infrared or in the UV. But on the other hand, you want the radiances in the UV part to be bright enough so that you can constrain CDOM. So the question is, when is the ocean dark enough that you can ignore it in the UV to constrain aerosol properties? And when is it bright enough that you can actually retrieve it to constrain CDOM? And so some of the studies were performed at these two wavelengths, because these two wavelengths were the initial wavelengths proposed for the 3MI instrument that was originally an instrument that was thought to be flown on this mission. So these are the questions that we focused a little bit on, and I'll go through this very quickly because it's very technical. So we did a lot of radiative transfer computations where we are including multiple scattering in the atmosphere and the ocean, and we are looking at variations in the ocean, changing things in the ocean. And what I was looking at was, well, what is the relative contribution of the ocean with respect to all of the contributions? How bright is the ocean in the UV? And if it is bright enough, does it really vary a lot? So we did a lot of sensitivity studies, and again, I'll go here very quickly through it. These are results at 350 nanometers, and shown here are polar plots. And polar plots is essentially a view of the ocean when you're standing on top of a very, very high mast of a boat. Yeah? And so you're looking around you and you can see the ocean. And the boat in this particular plot is pointing towards a sun glint. And if you would be looking towards the star direction, then you have the sun in the back of you. You'd be looking at the back scattering direction. And we're looking here at top of the atmosphere contributions of water-leaving radiances, the relative contributions. And if you go from left to right, what is changing in the simulations is the amount of phytoplankton. So if you have very little phytoplankton, the ocean is very blue. And as you're going to increase the amount of phytoplankton, the ocean is becoming dark. It's becoming greener. And if you're looking at the UV wavelength, becoming greener means it becomes darker in the UV. So that is what you see here, a darkening of the ocean because it becomes a darkening of the ocean in the UV because it becomes greener. And remember that this wavelength, they were hoping that the ocean was actually dark enough that it could be ignored, so that you could focus on the atmosphere only, constrain aerosol properties. But clearly for oceans that do not contain a lot of phytoplankton, and that's in the central gyres of the ocean, it becomes actually quite bright in UV. It becomes about 8%, and if you actually change the amount of CDOM in it, you can get variations between, let's say, 10 and 12%. That's noticeable at the top of the atmosphere. So not only can you not ignore the ocean, but you can actually even see variations in the ocean. Now that's of course good for ocean science, but not good for getting rid of the atmosphere, characterizing the atmosphere. So that was a problem. The studies that we perform for a polarimeter is to look at, well, what effect do we have if we're looking at the polarized radiance? Because essentially what is important to remember that all the light that we are seeing, it contains a polarized fraction and an unpolarized fraction. And that is true for the ocean, which has a polarized fraction and an unpolarized part, as well as the total signal at the top of the atmosphere. So rather looking at how much does the ocean contribute to the intensity that we see with our eyes, we could also look at how much does the ocean contribute to the polarized reflectance at the top of the atmosphere, or to the unpolarized reflectance of the atmosphere. It turns out that the radiation that is coming out of the ocean is quite unpolarized. So this component is very small. So if you just focus on this component here, you can actually make it darker, and that is what is shown here. So rather looking at how much does the ocean contribute to the intensity at the top of the atmosphere, you could look at how much does the ocean contribute to the polarized reflectance at the top of the atmosphere. Now you're seeing that the ocean is becoming much darker. You want the ocean to be dark enough here. So one of the things that we could do with the polarimeter is to just look at polarized reflectances. Therefore the ocean contribution becomes smaller, and you can focus more on the atmosphere. So that is some of the things that we're focusing on. We are also conducting now some field experiments. This is a field experiment that we've been conducting over the last 3 years, where we are flying a high altitude aircraft that contains our instrument, or I should say Brian and Michael's and the GISS instrument, the RSP instrument, that is measuring the polarization at many different viewing angles, 152, and at 9 different bands. And it was also carrying a hyperspectral imager that was obtaining radiances from 0.38 to 2.5 micrometer. And so we are looking at data that were obtained very high in the atmosphere, almost akin to satellite instrument observations, and to look at, well, if you have hyperspectral images and you add polarization to it, what can you do with it? So that is what we are doing now. We have, of course, theoretical studies, but we are also conducting sensitivity studies. So okay, so how can multi-angle polarimeter help ocean retrieval? Well, for open oceans, as I said, you can make the ocean darker, because normally the ocean is kind of blue, so it's not dark enough in the UV, in the open ocean. But if you look at the polarized reflectance, you can make it darker. So that is how polarimetry can work in open oceans. You make it darker, therefore you can concentrate on the atmosphere. But that's for open oceans. For coastal oceans, so-called case 2 waters, the waters can actually become very bright. And especially in the visible and sphere part of the spectrum, you can actually see the ocean even when you're looking at the polarized reflectances. And so you cannot ignore it anymore, but then comes the interesting question, okay, but can we then actually use it? Here we're using polarization so that we can make it darker. Here we can actually see the polarization of water-leaving radiance. Can we use it to obtain properties from the ocean? So that is also another thing that we were starting to look at. And I was fortunate enough to be at Amir Ibrahim's defense earlier this year, and he looked exactly at that. If you're looking at the polarization in coastal oceans, can you get information from the ocean, interesting information that you cannot get from intensity measurements? And I'll go through this very quickly because I'll just mention the important things, and I'll just show some of the results for the coastal oceans. And Russian scientists have already done measurements, and what they saw that the underwater light polarization, or the fraction of light that is polarized underwater, that it varies with this ratio, the extinction divided by the absorption in water. And there is actually a very nice sensitivity to that property. And why it is interesting, if that is true, and his simulation shows that that is indeed true, why this is very important is because if you can get this property from these measurements, then you have this ratio, extinction and absorption. If from other measurements you can get the absorption, which they can currently, then you can get an estimate of the extinction and of the scattering coefficient. Now, this is a quantity that cannot currently be obtained from intensity measurements. What you're getting is the so-called backscattering coefficient, but not the scattering coefficient. The things that Brian was talking about in terms of how to determine the different, not the different phytoplankton species, because for that you need the spectrum, but for instance to determine the total amount of carbon. For that you need the scattering coefficient. That they cannot get now, but if you add polarization, you might get this quantity and work your way through this quantity. So he showed that, well, if you use polarization, you might get something actually that you cannot get from intensities. And these were his simulations for underwater. These are for above water. He saw that actually it still exists above water. And he actually did even some simulations for the top of the atmosphere. And there he saw still some sensitivity. So he said, well, you know what, we could maybe use this. So this was of course all theoretical work, and what he did was he also did some field experiments, or participated in field experiments, where they measured the polarization of the underwater light and also of the skylight and water leaving radiance. And from that they used the method that he proposed to retrieve this scattering coefficient. They also made measurements, underwater light measurements of the scattering coefficient, and we're trying to see if they match with one another.
Now, the scattering coefficient is at the surface or even at depth in the
It would be at well, yeah, I mean, I would say it would be at the surface, or maybe if you're doing measurements on just above the surface, you can get some information about the depth. But you can imagine that if you're looking at the top of the atmosphere, it will be only, as you said, the top few 10 or 50 meters that you're getting. And well, here are his results. Actually, what he was doing is he retrieved the extinction coefficient from where you can get the scattering coefficient and compared it with in situ measurements. And he showed that actually you can get it. Now this is very interesting for the ocean color community, because they could not get this. And he's showing that you can get it with polarimeter. So that's why, and he's now a postdoc there, because they found this work very interesting. So they continued to do validation experiments with the cruise that was happening last summer, where they made measurements again for the underwater light polarization, the skylight, and our instrument participated in that. And we are still analyzing those data. Now the idea that you can use polarization in coastal oceans to retrieve something of the ocean rather than only atmospheric correction was actually investigated and shown in an earlier work where they used polar instruments to look at the polarized reflectance, and they looked at the total and polarized reflectance and showed that if you're looking at how they co-vary, you'll get some information about the minerals in the ocean. Now, they were not aware of the work that Amir Ibrahim was working on, but at least this is a real case example of real measurements with a polarimeter from space, where you show that actually for coastal oceans you get sensitivity to properties of the ocean, and you can use it, and that is what they did. So this is just my last slide. So in summary, for open oceans, for blue waters, you can use polarimeter to correct for the ocean in their terms. For our terms, of course, it is to retrieve the atmosphere and do research with that. And for coastal oceans, you can do actually a little bit more. You can actually try to retrieve new properties that you could not have been doing if you were just using a radiometer. So that is a little bit of the science that they are now looking at, and it's continuing.
Can I ask you something about the field campaign? So you presented something about that before, and if I remember, they had like all the different polarimeters on the plane, like 3 different ones. So was there any, a lot that could be learned by having them on the same airplane and the same campaign?
Well, Kirk Noble's piece is actually looking and comparing those data sets, and actually the purpose was to see, are they looking at the same things? What are the differences? So it was more, I think, focused on the comparison of the data instead of comparison of the retrievals. And Kirk is still working on it. I think that he found a very good relationship with intensities, but there were some questions that still needed to be resolved in terms of polarization. There are indeed 3 instruments that were 2 or 3.
3, but we've never seen data from one.
Okay. So
Is that one of the candidates? Or is that?
Not
No.
yet. That's Vandelay Martin's instruments from UMBC.
So Kirk has been looking at our aircraft data and the data obtained by the other instrument, and the intensity was quite good. The polarization, there remained some open questions that are still being worked on because there were differences there. Does that answer your question?
Yeah.
The measurements themselves are challenging.
Yes.
So unless you have the polarimeter in pace, you cannot really get a good sense of CDOM or coastal processes.
Oh no, you can. I mean, that's the reason why they are looking at the UV, because in the UV part of the spectrum, you get a high sensitivity to variations in CDOM absorption. You see those variations in intensity as well as in polarization. Sorry, so you see these variations mostly in intensity. The polarization helps you with getting the scattering coefficient. Not CDOM,
I think
scattering.
in terms of atmospheric correction, it's an open question how well you can do at absorbing aerosols. Because once you're trying to do coastal waters and you've got an absorbing aerosol, you need to know what its vertical distribution is in order to do the atmospheric correction. So you then need to do a good job in the ocean A band to try and figure out what the vertical distribution capacity is to then subtract it out. So your encircles are larger, but you can probably still do it.
Is a LiDAR helpful there? This is like one. It
would.
used to be part of the concept, right?
It would be, but for the ocean color, you have such a huge swath that you could use a LiDAR. You learn
Right.
everything.
What's the context? Because it's called pre-something.
Aerosol cloud ecosystem mission. So that's one of those massive decadal survey ideas for a mission, which was going to be just like a school bus filled with instruments, which was not really
Radar, LiDAR, imaging polarimeter. That was the idea, and it put the ocean people together with the atmosphere people, but that turned out to be a marriage that was not consummable.
Only we could build a LiDAR. That would save on one instrument at least, right? So I think they would like to change the name of the mission.
Well, not the abbreviation, but what it means.
Or both.
I mean, polarimeter and colour excellence.
Then they can only name it after they
How
have
about
it.
colorimeter for the atmospheric correction experiment.
Yeah.
I put my vote there.
That will happen.
Can you propose that?
You can put it in a cookie jar and see how it goes.
Get very much support from ocean people.
I don't think so. They are the boss.